Determination of the internal resistance of an electric cell by using potentiometer. In the diagram, this is a driving battery of EMF E prime, and to this driving battery of EMF E prime, an ammeter A is connected. Having ammeter has a negative and positive terminal, and this is the rheostat RH, which is also connected to the ammeter in series. And here we can connect a key K having plug can be removed. Now we can draw potentiometer wire having two terminals A and B. These are the two terminals A and B of the potentiometer wire. This is the driving battery of EMF E prime. Driving battery of EMF E prime, and RH is the rheostat or variable resistance rheostat, and E is the ammeter to measure the current. And rheostat is used to control the magnitude of current, and this is the driving battery of EMF E prime. And this is potentiometer wire AB, which is connected to the driving battery. To the terminal A, an auxiliary cell of EMF E, an internal resistance small r is connected. This is a galvanometer. To this galvanometer, a jockey J, a sliding clip jockey J is connected, and jockey J can be pressed at the point C1 of the potentiometer wire. An external resistance along with a key K1 is connected in parallel combination with the auxiliary cell of EMF E. R is the external resistance of this auxiliary cell. K1 is the key, J is the jockey. When it is pressed with the point C1 of the potentiometer wire, galvanometer shows no deflection and balance condition is obtained. When the plug is removed from the key K1, the auxiliary cell E comes in the circuit, jockey J is touched with the point C1 and galvanometer shows no deflection. And when the plug is inserted in the key K1, resistance capital R comes in the circuit, jockey J is touched with the point C2, and length of the portion AC2 is L2. Length of the portion AC2 is L2, and length of the portion AC1 length of the portion AC1 length of the portion AC1 is L1. L1. Let a constant current I be maintained through the potentiometer wire. Let a constant current I be maintained through the potentiometer wire through the potentiometer where AB made of constant and having zero thermal coefficient of resistance, potentiometer where AB, by using a driving battery of EMF E, driving battery of EMF E, of EMF E prime, not E, an ammeter A, an ammeter A, and a rheostat RH, respectively. Driving battery E prime, ammeter A, and rheostat are connected in series combination, and the rheostat RH respectively. L1 and L2 are the two lengths. An auxiliary cell of EMF E, an internal resistance small r, is introduced. An auxiliary cell of EMF E, an internal resistance R, is introduced with the potentiometer where AB, by using a galvanometer G, an auxiliary cell of EMF E and internal resistance R is introduced with the potentiometer where AB, by using a galvanometer G and jockey J. Also, an external resistance capital R, and a key K1, and a key K1 or K prime also an external resistance capital R and a key K1 are connected in parallel combination with the auxiliary cell of EMF E, capital E. If plug is removed from the key K connected to the external resistance capital R, then the auxiliary cell of EMF E, comes in the circuit. comes in the circuit. The plug is removed from the K1 connected to the external resistance capital R. The auxiliary cell of EMF E comes in the circuit. Now the jockey J is placed at the point C1 of the potentiometer where AB. If the jockey J is placed at the point C1 of the potentiometer where AB of the potentiometer where AB, the galvanometer shows no deflection. If the jockey J is placed at the point C1 of the potentiometer where AB and the galvanometer G shows no deflection. Galvanometer G shows no deflection. At this balance condition of the circuit containing the potentiometer and the auxiliary cell along with the resistance, at this balance condition of the circuit, potential difference between the two poles of the auxiliary cell of EMF E, potential difference between the two poles of the cell of EMF E, the bracket will be equal to the potential difference will be equal to the potential difference across portion AC1 of the potentiometer wire, across the portion AC1 of the potentiometer wire, potential difference across the portion AC1 of the length L1 of the potentiometer wire. Potential difference between the two poles of the cell auxiliary cell of EMF E equal potential difference across the portion AC1 of length L1 of the potentiometer wire. Now we can return to the diagram. So what about the potential difference between the two poles of the cell of EMF E? Now if jockey J is touched with the point C1, the galvanometer G shows no deflection. The jockey J is touched with the point C1 of the potentiometer where AB, galvanometer G shows no deflection and balanced condition is obtained. Galvanometer shows no deflection. So at this balance condition, voltage across this portion AC1, that is VAC1, will be equal to the potential difference across this portion containing the cell E, that is VAEC1. So on the left hand side, potential difference between the two poles of the cell should be VAEC1, VAEC1 containing the cell of EMFE will be equal to VAC1. Now VAEC1 is only the EMF E because this is the potential drop or potential difference in an open circuit as plug is removed, and VAC1 equal to KL1 because the principle of potentiometer, according to the principle of potentiometer, potential drop is directly proportional to the length. That's why the potential drop across the portion AC1 will be equal to KL1. This is not VAC, it should be VAC1 equal KL1, and K is the potential gradient of the potentiometer where voltage per unit length is called potential gradient of the potentiometer where. So we get E equal KL1, that is the EMF of the auxiliary cell. E equal KL1, equation 1. Now the diagram, now the plug is inserted in the key K1 connected to the external resistance capital R. The plug is inserted in the key K1. The plug is inserted in the key K1 and the external resistance capital R comes in the circuit in this closed circuit. External resistance R comes in the closed circuit because plug is inserted in the key K1. If the jockey J is placed at the point C2, of the potentiometer where AB, if the jockey J is placed at the point C2 of the potentiometer where AB, the galvanometer G shows no deflection. The galvanometer G shows no deflection. That means no current flows through the branch containing the galvanometer and the galvanometer. The galvanometer G shows no deflection, and the balanced condition is obtained. Again, valence condition is obtained once again. Now, at this balanced condition, PD across the external resistance capital R, PD between the two poles of the auxiliary cell in the closed circuit, between the two poles of the auxiliary cell of EMF E in the closed circuit. Initially, we had potential difference between the two poles of this cell in an open circuit because plug was removed from the key K1. But here plug is inserted, that's why it is closed circuit. and we can write potential drop between the two poles of the cell of EMFE in a closed circuit will be equal to the potential difference across the portion AC2 of the potentiometer, where potential difference across the portion AC2 of the potentiometer, where AC2 of the potentiometer where PD between the two poles of the cell of EMFE in closed circuit equal potential drop across the portion AC2 length L2 of the potentiometer, where so hence it should be VAC VR C2 equal VAC2. In this closed circuit, resistance comes in the circuit. V equal KL2. V equal KL2 equation 2. Here, the potential difference between the two poles of the auxiliary cell should be equal to the terminal voltage of the cell in this closed circuit. The plug is inserted in the key K1. That's why it is closed circuit, and potential difference between the two poles of the cell will be V. And here we get VAC2 as KL2 using principle of potentiometer. Potential drop is directly proportional to length, and we get V equal KL2. V is the potential difference across the two ends of the resistance capital R, and it is also the terminal voltage of the auxiliary cell of EMF E. Now we can draw the diagram of auxiliary cell separately. Here the external resistance and the key K1. This is the diagram of auxiliary cell. R is external resistance, E is the EMF, and small r is the internal resistance. V is the potential difference between the two ends of the resistance capital R, and V is also the terminal voltage of the EMF of the cell of EMF E and internal resistance small r. As external resistance capital R is connected in parallel combination with the auxiliary cell, that's why V and V will be same. We know that the internal resistance of the cell of EMF E is given by internal resistance of the auxiliary cell is given by R equal E by V minus 1 bracket close into capital R. E by V minus 1 into capital R equal, from equation 1 and 2 we can put the expression of E and V. E is the EMF of the auxiliary cell and V is the terminal voltage. KL1 divided by KL2 minus 1 bracket close into capital R. Therefore R equal bracket L1 by L2, lengths of ratio of lengths of the two portion AC1 and AC2 respectively, minus 1 into capital R is the external resistance. So small r equal L1 by L2 minus 1 bracket close into capital R. This is the internal resistance of the auxiliary cell of EMF E, which is connected to the potentiometer wire AB. Hence, knowing the values of L1, L2 and R, knowing the values of L1, L2 and capital R, values of L1, L2 and capital R. The internal resistance small r of the auxiliary cell of EMFE, the cell of EMFE can be determined can be determined